Okay, so all this is well and good, but how does it help us multiply arbitrary complex numbers that do not necessarily have this form? That's the next natural question. Because this is all beautiful, but it only works for this specific kinds of numbers, where the real part and the imaginary part are the cosine and the sine of the same angle. Well, actually, all that's required to make the real and the imaginary parts cosine and sine of the same angle is that their squares add up to 1. They just have to be on the unit circle. That's all that's required. Because if you consider the unit circle, then any number on the unit circle has x and y coordinates that are exactly sine and cosine of some angle. And not only is it of some angle, but it's specifically of this angle right here. So any other complex number whose real and imaginary parts do not add up to 1 in squares, you just need to scale it so that they do. Okay, let's see what happens. Okay, well, if we look at a number, a plus bi, I accidentally wrote a parenthesis because I was actually still thinking about William Hamilton's form of complex numbers, where it's just a pair of numbers. Because this interpretation as a point in the xy plane is hard to shake off, nor do we want to. So a and b, if you square them and add them together, add up to a squared plus b squared, not 1. So let's factor it out so that what's left adds up to 1 in squares. So you actually have to factor out square root of a squared plus b squared. So you factor out what we call the absolute value of the complex number. And then what we have left in parentheses is a divided by this quantity plus b divided by this quantity I. So it's a. And so now inside we have a number, a complex number, such that if you square its real and imaginary parts and add them together, you get 1. So this is a number of this form. It's just a matter, here comes my unit circle back. If you plot the real part along the x-axis and the imaginary part along the y-axis, it will end up on the unit circle right here. Okay? And so two numbers whose squares add up to 1 always correspond to the cosine and sine of some angle alpha. So we'll call that angle the angle alpha. And this angle is uniquely determined by these two values, basically by its cosine and sine. So think about this. Cosine alone doesn't determine the number because there are two angles. Cosine alone doesn't determine the angle because there are two angles with the same cosine. Sine by itself does not determine the angle because there are two angles that share the sine. But cosine and sine together determine this angle uniquely. Or almost uniquely. That's a great point that may seem not too significant right now, but actually proves the key to all the wonderful analytical and integral properties of complex functions. Because I can always add 2 pi to this value and get another legitimate value for alpha, so that if I plug it into this, I get back the same complex number. So my statement that sine and cosine determine the angle uniquely kind of needs to be modified. It's not 100% unique. It's subject to adding a multiple of 2 pi. So in order for it to be unique, we have to agree that the angle varies, let's say from minus pi to pi. And one of them has to be inclusive and the other one needs to be exclusive. And so the tradition is usually to make pi inclusive and minus pi exclusive. So let's write it down like this. So there's always this cut. I could have made it go from 0 to 2 pi, but I also could have made it go from pi over 2 to 5 pi over 2. And so there's always this cut. I always have to find the one angle where this stitching occurs. So this choice of pi, which is equivalent to minus pi in the angle sense, is the standard one. But I could have, so we cut it on the negative x-axis, but I could have cut it anywhere. So with that caveat, this angle is unique. And because of this caveat is why a lot of the complex magic happens, including the Cauchy residue theorem, which is one of the highlights of the course. But not as big a highlight as Euler's formula, which is still a leap away from this, which is coming tomorrow. Okay, so we'll call that angle alpha, and naturally we'll call this quantity r. And so this becomes, and this is called the polar form of complex number. And the polar form adds a whole new interpretation to multiplication of complex numbers. Here is what happens. What you have up here is the product of two complex numbers. Let's call it in Cartesian form, because once we draw them in the xy plane, this corresponds to the x coordinate and the imaginary part corresponds to the y coordinate. So I think calling this the Cartesian form is great. And it is what it is. The nice thing about the Cartesian form is that you can basically FOIL. You can use normal rules of algebra plus the rule that I squared equals minus 1 to work with complex numbers. That's great. But the polar form is great in its own way, because, as you will see in a moment, it makes for great algebra, but it also makes for a great geometric interpretation. Here we go.